Hello and welcome to my last video of my Capstone project. This is the second video on electrochemistry, and we're going to talk about electrochemical and electrolytic cells. Let's start by considering this redox reaction, and I separate it into its reduction and oxidation half reactions. We'll start by looking at electrochemical cells. An electrochemical cell is kind of like a device that uses spontaneous redox reactions to generate electrical energy. So the key thing is it's spontaneous. For example, we see that our reaction up here, if we look at our table, our half reactions, strongest oxidizing agent and reducing agent, it's downhill from each other. So this is spontaneous. So it can be used in an electrochemical cell. So now let's construct one together. It starts like this. We have two beakers, and then we have a piece of copper and a piece of zinc dipped into them, connected via a wire and connected to a light bulb. Now these pieces of metal are called electrodes, and they provide a surface for the reactions to occur. Now I know this doesn't make sense right now, but as we keep constructing this cell, it'll make more sense. In our solution on the left side, we have our copper NO3 And on the right side, we have our zinc NO3 And then in the middle, we're going to put what's called a salt bridge. And this salt bridge is going to be filled with KNO3. And the salt bridge allows for the movement of ions to bounce electrical charges. So what's really happening here? On our left side, on our left half cell, that's what it's called because each of these beakers, they stand for one half reaction. So that's a half cell. What's happening here is our reduction half reaction, where copper 2 plus is going to gain 2 electrons to form copper solid. On our right hand side, we have our oxidation half reaction, where zinc is going to turn to its zinc 2 plus while losing 2 electrons. So our zinc here is going to lose 2 electrons, right? Where the electrons going to go? The electrons are going to travel into this wire. So electrons travel here from our zinc and travels to our copper electrode. And then once the electrons get to this point, the electrons will travel through the copper metal and then react with the aqueous copper ions that are in this solution. Because we know that this solution is going to dissociate into CO2 plus and our NO3 minus. Same with our other side. And once this electron that came from zinc comes all the way here and reacts with this Cu2 plus in the solution, this is what's going to happen. You're going to be forming more copper metal. So what you'll see is an additional layer of copper being formed, like this. So our electrode for our reduction, that's going to be our cathode. And it's going to be positively charged because electrons are going towards it. You kind of think of it as if you had a positive end, it's going to attract a negative end. On our right hand side, that's going to be our anode. And this is where oxidation occurs. And it's negatively charged because it is a surplus of electrons. That's why we need to make the electrons go this way. Now let's look at the salt bridge. What's the salt bridge for? Well, we know that what's happening at the zinc electrode is that our solid zinc is going to turn into our zinc 2 plus. So we're going to be making more ions going into this solution. That means that our zinc concentration is going to go up. And if we look at our copper electrode here, or a cathode, we're actually gonna be getting rid of our copper 2+ because we're turning it all into our solid copper. So our copper 2+ concentration goes down. And that causes a lot of unequalness, you could say, in the charges. Because our anode would be very positively charged and our cathode would be very negatively charged. So that needs to be balanced out somehow. And that's where the salt bridge comes in. Our surplus of positive ions, such as our zinc 2+, can travel through the salt bridge over to this side. And our potassium, which turns into K+, and this turns into NO3-, our potassium ion can go to our cathode to balance out the negative charge, whereas our NO3- can go towards the anode to balance the positive charge. So in short, the salt bridge is for balancing this charge difference between the cathode and the anode. You could even say that it completes the circuit because our goal here is to light up this light bulb, and the movement of electrons actually does that. But you need a complete circuit for that to happen. So here's a quick recap of what's happening. Our zinc electrode here at the anode, it's going to turn into its ions plus 2 electrons. So our zinc metal is slowly going to decompose and die. And the products, which are zinc 2+ and electrons, our zinc will go into the solution, our electrons will go through this wire, power the light bulb, and go towards our cathode. In our cathode, our copper 2+ ions that are in the solution, they're going to gain the 2 electrons that just came from the zinc anode. And they're going to precipitate into solid copper, which is why we'll have a copper plated thing on top of that. So we're going to have more copper metal and less zinc metal. Now there's a lot of charge differences between the cathode and the anode. That's why ions would move through the salt bridge to balance that. And that's how an electrochemical cell works. Next is standard reduction potentials. And this is basically just addition and subtraction, which is why I'm going to skip it. It's very easy. Though the main thing you want to look out for is that you never multiply them. When you are multiplying a whole reaction to balance the electrons, you will not multiply your voltages. After you calculate them, if you have a positive E cell, then it'll be spontaneous. Otherwise, it'll be non-spontaneous. Next, let's look at electrolytic cells. These are kind of like the opposite of electrochemical cells because they use non-spontaneous reactions. And there are 3 main types of electrolytic cells, and I'm going to go through each of them. First, we have our molten salt. Let's say we had this redox reaction. NaCl, that's our salt, it's going to be in liquid form because it's molten, so very hot. Turn to our Na+, liquid, and Cl- liquid. Now one thing to look out for is that water does not exist in any of these molten salt problems. That's actually something that tricked me on the test, so make sure molten equals no water. And since there's no water, our Na+ is going to be our OA, oxidizing agent, and then Cl- is our reducing agent. Now we'll balance this using the half reaction method. Our reducing half reaction is Na+ plus E electron turns into sodium. Our oxidation is going to be Cl-, 2Cl-, turning it into Cl2 plus 2 electrons. And to balance the electrons, we multiply the top one by 2. And finally, we write out our equation 2 Na plus 2 Cl minus turns into 2 Na plus Cl2. And then our sodium is going to be solid, chlorine is going to be gas. Now let's actually draw out this cell. We only have one container this time. I'm going to use 2 inert electrodes, meaning they don't react with anything. We'll say this one is our cathode, and this one is our anode. They'll connect via a battery, and this time we need a battery because it is non-spontaneous and we need some sort of energy to drive the reaction. This side is going to be our negative end, this is our positive end. The electrons will come out of the negative end. Here we have our liquid Na plus and our liquid Cl minus, because if we look back to our original equation, this is what's happening inside molten salt. Okay, now we have to remember that reduction always happens at the cathode. So our reduction here is going to happen at the cathode. So it starts with electrons leaving the battery. It'll go this way, and then it'll go into the cathode, which is inert, so it will not react. So electron travels down here, and then it's going to react with our sodium ions in the molten salt, and that's going to form our solid Na over here. So around here we're going to have just some solid chunks of sodium. On our other side we have our anode, and here our oxidation reaction is going to occur. So our chlorine ions in the molten salt is going to go towards our anode, and then here it's going to deliver 2 electrons into the anode and then turn into chlorine gas according to this oxidation reaction. This is chlorine gas. So it's going to deliver 2 electrons. Electrons move up and back towards the battery to complete the circuit. And then our liquid chlorine ions is going to turn into chlorine gas, which would bubble up. So that sounds very complicated, right? And I probably didn't explain it very well. But the main thing you want to look at is you want to track the movement of electrons. So you're going to start from the battery and see where the electron goes. So you start by the electron leaving the negative terminal. So it goes into your cathode. It's going to do the reduction half reaction. And then on our anode, at our anode, it's going to do our oxidation half reaction. And then that's going to give away electrons, and we're going to track the electron back to the battery. Next is going to be aqueous solutions. It's going to be exactly the same situation, but you're going to have water included in your calculation. And where does that play a part? Because your water, you have to consider as possibly your strongest oxidizing agent or strongest reducing agent. So it's not for sure that you're going to use your sodium and chlorine for your reaction. You might have water being a stronger oxidizing agent or reducing agent. And that's basically the main difference. Everything else is the same. Finally, we have electroplating. And this is when you gold plate or silver plate or zinc plate or any of that for metals. And what's happening is you're actually depositing some metal straight to the surface of your cathode. In this case, our cathode is going to be this coin. And let's say we want to gold plate it. So what we do is we start with gold ions. And as this cell operates, we know the electrons are going to move this way, right? Towards the cathode, which is the item we want to electroplate. And our gold is going to gain this electron, and that's going to form solid gold. So we'll have a layer of solid gold around this coin. And as for our anode, it's kind of just there to sacrifice electrons, like to give electrons this way, so that the cathode can actually have it and then form the gold plate around it. Again, reduction is what happens at the cathode, and at the anode, that's always oxidation. Okay, well, that was very hard to explain. I apologize for explaining this unit so badly, but good luck on your test. It was fun making videos. Please like and subscribe, I guess. If you're only using this video to study, I recommend not doing that and actually using the notes, because that'll make more sense. But anyways, I hoped my videos helped you at least a little. And yeah, thanks for watching. That sums up my capstone project.